This is Mrs. Baisden, and today we're going to go over how to do acid and base calculations. So water can be described as amphoteric. So what that means is it can behave as an acid or a base. So anytime you have a sample of water, a small part of that water has dissociated into H3O+, which is called the hydronium ion, and OH-, which is called the hydroxide ion. So water undergoes something called self-ionization. So those two water molecules react to produce that H3O+ and OH-. So when you have pure water, there's only a very small amount of H+ and OH- present. So as soon as they dissociate, they go back together and reform water. When we're looking at acids and bases, we can describe their acidity or how much H+ is present by using something called the pH scale. So the pH scale you probably heard of before. You probably talked about this in grade school at some point. It goes from 0 to 14. So acids fall within the 0 to 6 range. Neutral is 7. Bases are 8 to 14. So if you look on that scale, you can see a lot of the common things that we're familiar with that are either labeled as acidic or basic. So something that would be the most acidic would be hydrochloric acid, which would be the same as the acid in your stomach that is used to break down food. You can see a lot of citrus fruits, lemons and oranges tend to be very acidic. Some other fruits, apples, bananas, tomatoes, those kind of fall within the 3 to 5 category. Water is a 7, like we talked about. Milk and blood also kind of fit into that same 7 category. Then as you get on the basic side, it tends to be more things that we would think of as cleaners. So soap is a 10. If you've ever had your mouth washed out with soap, you know that bitter taste that's associated with a base. Ammonia, sometimes that's it has a real distinct odor that can be used in cleaning products. Sometimes Windex has ammonia in it. So that tends to be on the basic side. And then drain cleaner or sodium hydroxide, oven cleaners, those types of things fall at the very high end of the pH scale where the most basic substances are. So because of the self-ionization, all acids and bases contain both H+ and OH- ions. If a solution is neutral, then the H+ and the OH- are equal to each other. And again, we label those as the hydronium ion and the hydroxide ion. An acidic solution is going to have a larger concentration of H+ ions, whereas a basic solution is going to have a higher concentration of OH- ions. If you have a strong acid or base, those completely ionize, or they completely split apart. So the concentration of that solution is equal to the concentration of the H+ or the OH-. So if you have a 1.0 molar HCl, hydrochloric acid, which is categorized as a strong acid, that's why you learned how to categorize strong acids versus weak acids last week. HCl, if you have a 1 molar concentration of it, because it completely dissociates or completely ionizes, the H+ is equal to the concentration of the acid. So if you have a 1.0 molar HCl, the H+ is 1.0 molar. If you have a base solution, same thing happens. It completely breaks apart. Now, what you have to be careful of is sometimes it dissociates or ionizes into more than one of those ions. So the HCl that we just saw, you only have one H+. So when HCl dissociates, you get H+ and Cl-. So that's why this 1 molar HCl was 1 molar, because there's only one HCl. When you have calcium hydroxide, if you remember doing this when you did your net ionic equations, you get Ca+2, and this 2 means that there's 2 OH-. So because of that, if it's a 1 molar calcium hydroxide, that generates 2 OHs, so you have to double it, so you get 2.0 molar. So that's the one thing you have to be careful of when you're making this assumption that the strong acid or base concentration is equal to the H+ and the OH-. You have to be careful of the formula to make sure if it's a 1-to-1, then it's going to be the same. But sometimes there's a 2-to-1 when it dissociates, and in that case, you would have to double the concentration of the initial substance. Okay, so when you do acid and base calculations, these are all the formulas that you're going to use. Which formula you choose depends on what you are given. So most of these calculations require to use a combination of these. So the best way to get used to doing these is just to do lots of practice. So over the next couple weeks, you're going to be doing lots of practice with these pH calculations. So the first one you can use is that H plus times OH minus equals 1 times 10 to the negative 14th. The pH is equal to the negative log of the H plus. So if you have the H plus, you can get the pH from there. The POH is the negative log of the OH minus. The H plus is the anti-log or the second log on a lot of calculators to the negative pH, or you could say it's 10 to the negative pH. OH minus, the anti-log, the second log, or 10 to the negative POH. And then finally, pH plus POH equals 14. So we're going to go through a couple of example problems so you'll see why there are so many of these different formulas, because it kind of depends on what you're given, and then you go to your list and you decide which of those formulas you need. So we're going to go through most of the different types of problems that you could be given so that you can see how all of these different formulas would be used. So for these first two example problems, this would be if you were given the strong acid or the strong base concentration. So this one says, what is the pH and POH of a 0.1 molar solution of HCl? Okay, so my HCl concentration is equal to 0.10 molar. HCl, I know, is a strong acid. So again, this only works if we're dealing with strong acids and strong bases. That's why you have that list of strong acids and strong bases. So that's a strong acid. And when HCl breaks apart or dissociates, I get 1 H plus and 1 Cl minus. So that means the concentration of HCl equals 0.1 molar. So that also means my H plus equals 0.10 molar. Okay, so from there, I want the pH and the POH. So if I go and I look at my formulas, I can use pH equals negative log of the H plus. Okay, so this is one of my formulas that I was given. So all I have to do here is take the negative log of that H plus. So negative log of 0.10. So when I put that into my calculator, the pH is equal to 1.00. Now pH values are kind of weird because they're based on log values. The sig figs for a pH value don't start till after the decimal. So this number here has 2 sig figs, so I would report this as 1.00. So that would be my answer for this one. This one also wants the POH of that same solution. So again, I'm going to look at my formulas. For this one, I know that pH plus POH equals 14. So I have the pH. So I'm going to sub that in. So the POH would be equal to 13.00. So that would be my final answer there. And again, when you're doing these, take a second and do a logic check. So since we know that acids have a pH below 7 and bases have a pH above 7, we know we're dealing with hydrochloric acid here, so that should be a low pH. And if I look down here, my pH is 1, so that makes sense. Okay, so here's another example of the same thing. So for this one, I want the pH and the POH of a 0.02 molar solution of calcium hydroxide. So I know calcium hydroxide is a strong base, and when it dissociates, I get a Ca plus 2 and 2 OH minus. So for this one, if the concentration of the calcium hydroxide is 0.02 molar, and there's 2 of them, the concentration of the OH minus for this would be 0.04 molar. Okay, now I'm going to go to my formulas. Now the way that I'm doing these two is one way, but there are other ways. So you could use other combinations of those formulas that you have, so don't feel like you have to do it exactly how I showed you how to do it here. Just know that most of these questions that you're doing will have more than one way to get the same answer. So for this one, since I have the OH minus, I'm going to use POH equals the negative log of the OH minus. So negative log of 0.04. So the POH is 1.40. Again, 2 sig figs. Sig figs don't start till after the decimal, so that's why I have to leave that 0.40 there. Okay, I also want the pH, so I'm going to do the same thing with the other one. pH plus POH equals 14. So pH is what I want to solve for. POH is 1.40. So when I solve for the pH, it is 12.60. Okay, again, 2 sig figs after the decimal. That does make sense. I know calcium hydroxide is a strong base, so it should have a high pH. 12.6 fits that description. Okay, the next type of problem is you could be given the pH or the POH. So again, for this one, I want to know what is the H plus and the OH minus of a solution with a pH of 8.25. So I have a pH value. So I can use that. I can use my H plus equals 10 to the negative pH to solve for the H plus. So 10 to the negative 8.25. And to do this on most of your calculators, you're going to hit second log. So that's where you find that 10 to the x. So when I solve that, my H plus is equal to 6.00. I have 2 sig figs here, so 6.0 times 10 to the negative 9th. Now, when you're reporting concentrations, you have to remember to put a unit on those. So this would have the unit molarity. Okay, now I also need the OH minus, so I'm going to go back to my formulas. I know that H plus times OH minus equals 1.0 times 10 to the negative 14th. So I have 6.0 times 10 to the negative 9th times OH minus equals 1 times 10 to the negative 14th. So if I solve for OH minus, that is 1.7 times 10 to the negative 6 molar. So then that would be your answer for that. Again, concentrations, those brackets mean those are concentrations, so concentrations have to have molarities. Okay, so here's another given pH or POH. So this time we're given the POH. So for this one, you go look at your formula list. I know that OH minus equals 10 to the negative POH. So 10 to the negative 1.75. So my OH minus would be 0.018 molar. Same thing I did with the last one. H plus times OH minus equals 1.0 times 10 to the negative 14th. This time I'm solving for H plus. OH minus I just solve for. So the H plus equals 5.6 times 10 to the negative 13th. Okay, so that's the second type. The last type would be if you're given H plus or OH minus. So these are probably the easiest, unless it's asking for multiple things. So for this one, if I have the H plus, then I know that pH equals negative log of the H plus, again, from my formula sheet. So negative log of 2.0 times 10 to the negative 7. Put that in the calculator. pH for that one would be 6.70. Okay, and again, pH values don't have units. The only time you have to worry about a unit is if you're reporting a concentration. Okay, so that would give you the pH of that particular solution. Last one. What is the pH of a solution with an OH minus of 5 times 10 to the negative 7? Okay, again, formula sheet tells me POH equals negative log of the OH minus. So negative log of 5 times 10 to the negative 7. So the POH would be 6.30. Okay, now this is one you have to be careful with because it wants pH. All I have here is POH. So this one is going to require an additional step. So I go back to my pH plus POH equals 14. I want the pH. I have the POH. So subtract that from 14. My pH is 7.70. And like I said before, these take a lot of practice, but once you do a lot of practice with a lot of different variations in problems, these are pretty straightforward and easy to do.